Hello and welcome to Calculus Tutorial. Today we are going to take a look at something brand new with our function analysis, and we are going to be saying something that I have yelled at you and told you not to say up until now. And we're going to look at this new thing called concavity and points of inflection. They're all sort of related. Once you know what concavity is, you can start studying these new things called points of inflection as well. All right, so let's start with some function analysis to see where this all starts. So, what do these two graphs have in common, and what is different between them? So first, what do they have that is the same? Well, first off, I hope you see that they are both below the x-axis, which means they are both negative. All right. Then, as you can see, both graphs are going down. And so the vocabulary there is they are both decreasing. Kind of the main things we've been looking at so far. Yet if they're both negative and they're both decreasing, why do they look so different? What is it, what characteristic about them makes them so different? Well, let's take a look at their slopes. That's what we've been studying this semester. So take a look at the slope here, and then go on down the graph and take a look at the slope here. As you go along the graph, the slope is very small. It's negative, so it's a very small negative. But then as you go, it becomes a much steeper negative slope. It's a bigger negative number. Whereas if I take a look at this one, we start out with a fairly steep slope, but then as we go, the slope gets shallower and shallower. All right, it gets closer to zero. And so if we want to describe that, it gets a little confusing because these are decreasing functions, but because the slope was a small negative and then became a larger negative, this slope is decreasing. I know that the overall magnitude of the number is getting bigger, but a bigger negative is smaller. So you are decreasing, the slope is decreasing, which I know I have not let you say that sentence before because it means something very specific, and we're going to take a look at what that specific characteristic is. And here, our slope is a negative number, but then it becomes a smaller negative number and a smaller negative number. And if your negatives are getting smaller, that means your slope is increasing. And so when your slope is decreasing, it makes your curve look a certain way. And when your slope is increasing, it makes your curve look a certain way. And we call this new thing concavity. Okay, put a line, these are no longer the same. Concavity. This curve here, think of the cave as pointing down. The cave is facing down. This is concave down. It'll become pretty easy to recognize when your curve is opening downwards. And this one over here is concave up. The cave is facing up is the way we want to think about that one. All right, so anything that looks kind of like this is concave up, and anything that looks somewhat like this in some way is concave down. And that's why I've never let you say these words in the same sentence before. If your slope is decreasing, what you're really telling me when I translate that is concave down. And if you say the word slope and increasing in the same sentence, what you are saying is concave up. And since we hadn't studied this yet, I did not let you put those words in the same sentence. All right, let's take a look at an example of that here. So now that we know what concavity is, let's take a more in-depth look at concavity. We'll do some work with some equations here in a second, but first, since we learned some new things, let's put this on our graphic organizer. So if I have a function f prime, and f double prime here. So we learned this new thing, concave up, I'll abbreviate that CU, and concave down. And what we said there is if you're concave up, that means your slope, the derivative, must be increasing. And if you're concave down, that means your slope must be decreasing. Well, here's the thing I like about this graphic organizer is you should be able to tell me what goes here now. If this function is increasing, that means the one directly to the right of it must be positive. And if this function is decreasing, that means the one right to the right must be negative. So when I ask you a question, determine the concavity of a function, I want to know, is this concave up or concave down? Well, that's going to be kind of hard to see from an equation. Even increasing and decreasing is hard to see from an equation. But positive and negative is much easier. So whenever you want to find concavity, the easiest thing to do is to look at the second derivative. So if I have an equation, I want to know the concavity, I'm going to take the first derivative. Let's see, negative 6x plus 4. And then I'm going to take the second derivative, which in this case will simply be negative 6. And so if my second derivative is negative here, that means my original function had to have been concave down. So this one would have been concave down. All right, next one. What is the concavity of this one? Well, we take the derivative. And I'm going to practice the chain rule here. Yes, we could multiply this out, but I'm going to practice. So we do 2 times the inside stays the same, times the derivative of the inside, which is negative 2. And let's see here. I'm going to rewrite this. Oops. So I'm not taking another derivative yet. That is negative 4 times 5 minus 2x. This one I would say you might as well rewrite this as negative 20 plus 8x. And so if we take the second derivative now, that is simply 8. And so the second derivative is positive. That means this one will be concave up. Okay? So if you want to find concavity, you want the second derivative. All right. Well, this brings one more thing that we can take a look at. Something called a point of inflection. So we have this thing called concavity, and that leads us directly to what are called points of inflection. Because a graph doesn't have to just have one single concavity, like the ones that we looked at. It could have multiple concavities, and the point of inflection is where you change concavity. Okay, so just this time I'll give us a graph of this so we can visualize it. So I'm hoping you can see that this part of the graph here, definitely concave down. But this part over here, definitely concave up. And so somewhere between these, we must change concavity. And that is called your point of inflection. One of the things I want you to be able to find. So think about that with our three graphs here. What would a point of inflection look like? That means we are changing from concave up to concave down, or vice versa, which means our derivative would have to be going from increasing to decreasing, or vice versa, which means our second derivative must be going from positive to negative, and in between those it must be 0. And so hopefully that looks familiar. We've done that before, but we've always done it with f prime. We've never done it to f double prime. And so we're going to do a very familiar procedure here, but we're going to be doing it to the second derivative instead of the first derivative. All right, so we need to find the second derivative. So y prime is equal to 3x squared minus 18x plus 2. And our second derivative is equal to 6x minus 18. Now, this is going to happen where our second derivative is equal to 0. So set that equal to 0. Solve that, add 18, divide by 6, you get x equals 3. Now here's one thing. We obviously have a point of inflection. It's right here now. We know it's at x equals 3. I gave you the graph so you can see it. But if you don't have the graph, you do have to check to make sure this is in fact a point of inflection by doing a sign chart. So put 3 here. Does this equation actually change concavity? So now you're going to plug in numbers to the left of 3 and to the right of 3, but you're going to plug them into the second derivative to make sure the second derivative changes sign. Now we could go from positive to negative, or we could go from negative to positive. We don't really care. Whichever one it is, you're going to have a point of inflection. So, if we plug in a number like 0, 0 minus 18 is negative. And if we plug in a number bigger than 3, like 5, 5 times 6 is 30, minus 18 is a positive number. So now we do know we in fact have a point of inflection, because this negative is a negative for the second derivative, and that means concave down. And this positive is a positive for the second derivative. And if your second derivative is positive, that means your function is concave up. And we are changing concavity. Concave down to concave up. We are, I've got it written right here, changing concavity. Sometimes that does not happen. If you go from positive to positive, you didn't change concavity, and you don't have a point of inflection. All right, so 3 is our point of inflection, so we sometimes abbreviate that POI, point of inflection, and you can see it quite clearly. 3 really looks like where we change from concave down to concave up.